Okay, so what if I told you that there's one single formula, just one, that can describe a booming population and tell you the age of an ancient fossil? Sounds kind of crazy, right? Well, today we're going to unlock that exact piece of math. Yeah, it totally sounds like a riddle, doesn't it? But the answer? Well, it lies in this one really elegant mathematical model. It's what scientists use to look way back into the past and, believe it or not, even predict the future.
And that's because this model is basically a universal code for change. Think about it. It works for any situation where the speed of change depends on how much stuff you already have. So it doesn't matter if you're an archaeologist digging up ancient bones or an epidemiologist tracking a virus. You are both using the exact same fundamental math to get your answers. How cool is that?
And here it is, the star of the show. N of t equals n sub 0, you'll often hear that called n naught, times e to the power of kt. Now, I want you to get real comfortable with this formula because it is the absolute key to everything we're going to tackle today. All right, I know what you might be thinking. That looks a little intimidating, right? All those letters and symbols. But trust me on this one. Once we break it down piece by piece, you're going to see just how simple and honestly, how powerful it really is.
So first up is N of t. The easiest way to think about this, it's your after picture. It's the amount you end up with, the final quantity you have after a certain amount of time has passed.
Okay, next up is n naught, or n sub 0. If n of t is the after picture, then this is your before picture. It's your starting point. Simple as that. How much did you have at the very beginning when time was 0? That's your n naught. And t? Well, t is pretty straightforward. It's just time. But here's the crucial thing, and you've got to remember this. Your units for time have to be consistent all the way through the problem. Super, super important. All right, now for my favorite part, the variable k. This is the rate constant, and it is truly the engine of this entire formula. It's the powerhouse. It controls not just how fast things are changing, but also in what direction. And this is where the magic of k really shines. It's so simple. If k is positive, you've got growth. Things are getting bigger. But if k is negative, you've got decay. Things are shrinking. That one little minus sign, it literally flips the entire story. It changes everything. Okay, enough theory. The best way to really understand this stuff is to see it in action. So let's roll up our sleeves and apply this formula to some real-world problems. All right, here's a classic, a bacteria growth problem. We're starting with 100 cells, and we know they double every 3 hours. So the mission, should you choose to accept it, is to figure out how many bacteria we'll have after 5 hours. Okay, step 1 is always to find k. Now, since the problem gives us a doubling time, we can use a really handy shortcut. The formula is just k equals the natural log of 2 divided by that doubling time. So for us, that's the natural log of 2 divided by 3, which gets us a k of about 0.231. See, not so bad. Now we can build our full model. We just plug in our k and our starting amount, which was 100. Then we just pop in 5 for t. And a quick calculation tells us we're going to have about 317 bacteria. Done. All right, let's switch gears and look at a decay problem. We're going to be working with carbon-14, the stuff archaeologists use to date really old things. So we know its half-life is a whopping 5,730 years. The question is, if we start with a 10-gram sample, how much is going to be left after 2,000 years? You guessed it, our first job is to find k. And hey, just like with doubling time, there's a shortcut for half-life too. This time, k is the natural log of 0.5, or 1/2, divided by the half-life. So we take the natural log of 0.5 and divide it by 5,730. And look at that, it gives us a negative k value, which is exactly what we expect for a decay problem, right? So we plug that k and our starting 10 grams into the formula, set t to 2,000, and we find out that after 2 millennia, about 7.85 grams will still be there. Okay, now for what I think is the most interesting kind of problem. We're flipping the script. This time, we know how much stuff is left, but we don't know how much time has passed. We need to find the age of a fossil that only has 40% of its original carbon-14 remaining. So let's set this up. The final amount, n of t, is just 40% of the starting amount, n naught. So we can write that as 0.40 times n naught. And right away, something really cool happens. The n knots on both sides just cancel each other out. So now we have 0.40 equals e to the negative 0.000121t. The problem is, our t is stuck up there in the exponent. How do we get it down? Well, we use its inverse operation, which for e is the natural log. So we take the natural log of both sides. That lets us pull that whole exponent down, and suddenly we have a much friendlier algebra problem. We just divide, and we find that t is about 7,570 years. That's the real magic here. We just used math to look back in time.
Okay, this formula is obviously super powerful, but it's also really easy to make a tiny mistake that throws the whole thing off. So let's go over a quick mental checklist you can use before you even start calculating, just to make sure you get the right answer every single time.
First thing, check the sign of k. Is it a decay problem? K has to be negative. Simple. Second, check your units. If your half-life is in years, does your time t match? They have to be the same. And third, double-check your initial amount, your n naught. Did you pick the right number to start with? If you nail these three things, you're going to be in great shape.
So why does all this matter? I mean, beyond just passing your next test. It matters because mastering this model, it's not just about precalculus. It is the foundation for a ton of more advanced science and math down the road.
For example, take a look at Newton's law of cooling. Now, at first glance, this looks way more complicated, right? But look closer. See it? Right there, at the very heart of the formula, is our old friend e to the kt. This is the exact formula that forensic scientists use to figure out time of death, just by measuring how a body cools down. It's the same exact principle of exponential decay, just dressed up a little differently.
And hey, if you're planning on taking calculus, you need to get really comfortable with this model, because I promise you, you are going to see it again. Calculus is all about understanding how rates of change define the world, and this formula, it's a cornerstone of that whole idea. Seriously, mastering it now is going to set you up for some major success later.
So there you have it. One single, elegant formula that can look back in time to date ancient artifacts and look forward to predict future populations. In a way, it's kind of like a mathematical time machine. So the only real question left is, what will you solve for?